तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we were looking at a very simple nonlinear problem, and we had worked out for the first increment the complete iterations that are required so that the convergence results are with us. Then we started with the next increment, and we had completed one iteration of it. In other words, what we were trying to do is that we have a big loop, okay, which is we called as the incremental loop, and there's another loop inside which is called as the iteration loop. So we had finished one here, and we had finished this and saw that convergence was attained. So we are in the second loop. Without wasting much time, let us look at the final results and make certain very important observations which would go a long way in seeing or in understanding the nonlinear analysis. Now let's come to the iteration 2 for the same problem. That is, this is increment 2, iteration 2. So I have calculated already the tangent stiffness matrix, then du2. Note that du2 is this increment in u for this particular iteration. Sigma of du's was the ones which gave us delta u. Then I calculate the u, epsilon, sigma, calculated the error. The error has obviously dropped. Okay, then we go ahead from iteration 2 to iteration 3 using the error to be the load or the right hand side, right? Remember, that's what we did. So now what I do again is to calculate this stiffness parameter, actually stiffness matrix. In this case it happens to be just one number because of the type of problem we are doing, and then we calculate du2 for the third. Look at that, it is the third iteration for the second increment. Already I know that you would have been exasperated looking at this problem and doing this. So you can imagine that if there is a simple problem like this with only one element, just one element, and not a very complicated stress strain relationship, and if this is going to take the kind of calculations that are involved here, these are the calculations that are involved for this simple problem, and imagine the amount of time that is required to solve a much more complex problem using the nonlinear analysis. So we calculate u, calculate epsilon, calculate sigma, and calculate the error. Go to the iteration. Hopefully this is the last iteration. Calculate kt and repeat all these steps so that ultimately, thankfully, the error is quite small. Now there are some very interesting observations you can make. Number one, look at kts. In fact, compare kts with what we have got in this, say, iteration, and even in this increment, okay, and compare them with the kts which you had got in the previous increment. Have a look at that. What is it that you see? What was our first kt? If you remember, what was our first kt? 2.4. Oh, sorry, 4. Yeah, it was 4.0, if I remember right. Yeah. So 4.0, we started it from 4.0. Look at the way kts have dropped. Okay, 4.0, 1.552, and now we have got 0.816. This is not a very good trend, and this is what happens many times in finite element analysis. when you look at these kind of problems. At one time, this is going to be so small, it's going to be so small that convergence becomes difficult. In fact, if this happens to be a multidimensional case, K would become ill-conditioned. So you can't apply whatever step you want. In other words, what it physically means for this problem is that the slope of this curve, which is very nicely sitting here with the value of 4, is now dropping. It's dropping. So once it drops like that, obviously Kt, which depends upon this Et, of course you know the sigma versus epsilon. So Kt, which depends upon the slope of this curve, is going to become smaller and smaller. And note that when I calculate the second step, this Kt happens to be in the denominator here. In other words, in actual multi-dimensional case, that is 2 dimensions or 3 dimensions, I have to calculate Kt inverse. Though you may not explicitly do it, you can say that you have to calculate that in order to solve for du. And this calculation, number 1, okay, poses a lot of problems when K becomes singular. Of course, you can't do it, and even if it's not singular, and even if it's ill-conditioned, this kind of things pose problem, and so convergence becomes difficult. So these are the difficulties that we are going to have. But of course, I'm not saying that every problem will end up in a situation where you can't solve. It would so happen that thankfully when we have a lot of elements and when the deformations are inhomogeneous, somehow Kt would still keep going. In other words, when deformations are not the same at every point, the stiffness matrix that are formed due to these elements would be such that it would be better than what we are seeing. Okay, now here there's only one element, so you have to understand that many times one element problems are more difficult than when we have more than one elements because of the inhomogeneous type of deformation. What is inhomogeneous type of deformation? That means the deformation is not the same in every element. Okay, this is what we call as inhomogeneous behavior. If the behavior itself is different from one point to the other, okay, they are not the same. 2 points are not the same.
Sir, the error depends upon the shape of the stress strain curve.
Yes, in other words, the error, okay, and hence the number of iterations that are required depends upon the shape of the curve. In other words, the question is it that we have taken 4 iterations, and if I have the same step and then in other words same step in the sense that same size of loading in the next step, I go to step 3, say I put another 2.4, will I take more number of iterations? Of course I will take more number of iterations, because as I move towards this period or these positions where the Et happens to be smaller and smaller, my time or my time step or my load step, both of them being the same, have to reduce. So for example, if you are going to do a linear problem, yes, I can look at a linear problem like nonlinear problem as well. In other words, I can say that I would go ahead and do convergence tests in a linear problem. Obviously, you will converge in the next step, because when you move from, say, this step here to here, okay, so you would require only 2 iterations. Why the second iteration? Because I have to calculate the error and compare it with the first one. So I would get a beautiful answer in the first iteration itself. Second iteration will have an error equal to 0, and I will say that I have converged. Okay, so many packages till very recently look at even a linear problem like a nonlinear problem. Is that clear? Yes, what is the question? Yes, epsilon is 3.998. There's a very small increase in the 0.3998. Right. Okay, now not 3.998, okay, 0.3998. Yes. Now, having understood how nonlinear problems work, let us now go back to the elastoplastic case. There were very interesting questions, and see how these questions can be answered from an algorithmic perspective when we do finite element analysis. Okay, any questions on what we did? Now, if you notice, in this case, what we did, there was one step to calculate stress. Now, the problem is not going to be very simple when I do an elastoplastic case. Just for simplicity, we assume a bilinear case where we say that there are only two slopes that operate, and that a well-defined yield point exists. Now, please note that this is a simple assumption. Okay, we can definitely modify it. We are going to do that later. But in order to understand the issues, I'm going to just look at this as a bilinear problem. I already made a lot of comments about the slope. It has to be, I mean, this is exaggerated. It has to be very close to the y-axis and so on. Now, what are the issues? The issue is that when I have this incremental loop and an iterative loop, at one point I have to calculate the stress, right? And this stress calculation, which is called a stress update in the literature, or stress integration, poses certain difficulties. Now, what are the difficulties? Assume that I am at this point here, when I am in n, okay, and I have to move ahead in stress. Okay. Assume that my deformations during that step is such that the epsilon that I get, okay, make me move from the elastic region into an elastoplastic region. It means that, let's say that that is what I get as delta epsilon, and that when I move my stress, I have to move from this point to the other point. So, what's the difficulty? The difficulty is that I have one slope or one type of behavior till I reach this yield point, and another type of behavior as I move out of this yield point, right? So, this problem, though it looks very straightforward or in a one-dimensional case, because of the fact that I have drawn very clearly and shown you this, is very subtle and involves lot of issues when you look at it in a multi-axial case. In fact, this had prompted quite a few researchers to work on the stress update algorithms, and a series of papers have been published from about maybe late 70s to the late 80s. In fact, though the first paper on stress update appeared way back in 1964, there have been a series of papers which had looked at the stress update algorithm very closely. Now, what are the other issues? There are other issues as well. I have to calculate the stress such that it lies on the stress strain curve. In a multi-axial case, we would see that this means the stress would lie at the yield surface. I can't get a stress at this point for that strain. So, I have to see that I lie on the curve. So, this is what we would call as consistency condition, and consistency conditions also have to be satisfied, okay? And you will understand the problems exactly now as we go along. Okay, so I'm going to take off from this point. In other words, I've already calculated delta epsilon, okay, till that previous step, okay, and we will look at a one-dimensional problem and deviate from here, okay, and see how we calculate the stress. Okay, clear? Okay, the first step is that we invest all the strains what all we have, that is delta epsilon, which we have calculated here, as if it is elastic. This step is called as the elastic predictor step. Is it clear? Elastic predictor step. So the first thing is that we will go to elastic predictor. So of course, before that we had the other steps. If you want, we can write that down also so that you are clear about it. So let me write down those steps. A, I calculated psi, okay, and then B, I calculated delta U, right, and I calculated delta epsilon, right. That's the step which I did. Then C, I do an elastic prediction. Now I made some comments on delta epsilon. If you remember right, I said that I would all the time start again and again from the previous converged value of u, and then calculate delta epsilon not based on du and sum it up, but I would base my calculations on delta u and then put that as delta epsilon. Right? This is what we said. Keep that in mind. We will make more comments on it as we go along. So the first step is that I do an elastic prediction. What is elastic prediction? That means that I get an estimate. People call this by different names. People say that it's a trial stress or an elastic estimate, okay, by saying that this delta sigma, okay, we will say sigma E, what sigma E is in a minute. Delta sigma E, okay, that is the elastic estimate of delta sigma to be E into delta epsilon. This is one dimensional case, so just I am putting that as E. In fact, there is no harm even removing this, okay, because it is for illustration purposes. We are going to only look at the stress strain curve. Okay. So what I have done is to say that I am going to invest all these things in the elastic case. So what do I do? Now I calculate sigma E to be sigma at the previous converged step plus delta sigma E. Is that clear? Okay. Now come back to this graph and see where we are actually. We are there because I have extended the slope directly. I mean, though it's a very, very special case, there are other cases that exist, so we have to exhaust all the cases as we develop this algorithm, right? So I'm not going to write down all the steps here, but it will be clear as we go along. As we go along, it will be clear, but I would like you to follow these things, and then maybe when we do a problem later, okay, we can put down all these steps in a more cogent form. Now, there are a number of cases which may happen at this point. What are the cases? Now, though I have just drawn a figure like that, this may not be the case. This may be one of the cases that may exist. There are many other cases that may exist. Now, there are two things that are possible. One is that the previous step, that is sigma n, can be in the elastic region like what we have said, or it can itself be in the plastic region, which means that when I have a curve like this, I may start my whole sigma n sitting at that point. This may be my sigma n. Note that I'm going to call this as initial yield, because that yield point is going to change. Is it clear? Okay. So there are two possibilities. I may be in the elastic region, or I may be in the elastoplastic region. That's my first thing. My second possibility, or second issue, which results in two possibilities, are that this elastically predicted case may be such that I may still be in the elastic region, or I would have gone to a plastic region in this case. Okay. In this case, I may march ahead in the elastoplastic region, or I would have come back and I would have been in an unloading curve. Right? So there are two cases initially, and each one has two other cases. So we have to look at all the cases in order to develop the algorithm. Is it clear? Any questions?
So this algorithm will be going to apply in the general form, because these cases arise only when we were talking about these cases when we were switching over from elastic region to plastic.
No, that is correct. So does this case arise only when we are looking at a situation where we are going from an elastic to plastic? That's exactly what I said. Going from elastic to plastic is only a special case.
It should be applied to
General case. The general case is such that I can go from elastic to elastic, I can go from elastic to elastoplastic, I can go from elastoplastic to elastoplastic, or I can go from elastoplastic to elastic. How do I do that? Unloading. So I have to consider all the four cases. Yes? We have not yet come to KT definitions. Okay, that's one of the things that we are going to find. Okay, so you will see that there are a lot of small tricks that we are going to do. In other words, the question is, what will happen if I sit exactly there? In most of the problems, it's almost impossible to sit exactly at that point. To give you a small insight into program development, what we usually do is we take that point and give a small band. See, if I say that the yield strength of the material is 300.2 Newton per mm squared, or 30.02 kgf per mm squared, sorry, MPa, in terms of MPa, just say 300.2 or 30.02 kgf per mm squared, then it is impossible for me to exactly hit that point, okay, because we are doing a numerical process, okay, and it would so happen that you may be either slightly below this mark or above that mark. Okay, so we will define a small band there for you can choose this as a. So it is not, that is exactly what we do. Is it possible to have a smooth variation? That's exactly what we do. We say that yielding takes place usually when it is in a small band. We will discuss this especially when we come to a multi-axial case. This is going to be an issue there, small issue, implementation issue. We will discuss that at that point. Okay? So let's understand first the broader aspects here. Now, so these are the four cases. So in order to handle these four cases, we first, what we do is to have an elastic prediction like this. That will settle us, that will settle our position. Okay, that will settle where we stand in one of these four cases. Let us see what we have to do when we get into one of these 4 cases. Of course, the problem is very simple if we go from elastic to elastic. It's not a problem at all. But what happens when we move from elastic to elastoplastic and plastic to plastic? We will right now see that the elastic to elastoplastic is a more general case of elastoplastic to elastoplastic. The other case, elastoplastic to elastic, which is unloading, is also very similar to the first case. It's not a problem. So, in other words, what do we do to find out these cases? Simple. Check sigma n and see whether sigma n is less than, we will include his case, so we will say that less than equal to sigma y. So, we will say that it yields when you just cross sigma y, and so if this is the case, then we say that it is elastic. Okay. So, in order to do a stress update, we need to check this as well. Now, let us say that, let us consider one case, most difficult of these cases. Let us say that this results in elastic, I will say yes, in other words. Okay, that is the first thing. Then what do? We check sigma e and see whether sigma e results in a what? In the plastic state or elastoplastic state. Why am I calling this as elastoplastic? Is there any, why is that I am not saying just plastic state? I can say that as well. No, the point is that it's not just coming back to elastic case, that's one thing, but more important is that I am not assuming that the elastic strains are negligible, absolutely. So, I am not assuming like that, and I am saying that there is an elastic strain which we will take into account as we go along, right? Okay. Now, so what do? So, we find out with sigma e whether sigma e has now crossed the yield point, right. So, whether sigma e is greater than sigma y at n. I specifically put sigma y at n basically because I can have a loading, unloading and reloading. Note that carefully. For example, coming back to this figure here, you see that I can go from this point to this point, that is fine, that is very easy to understand. But you can have a situation where you would like to look at a loading pattern where there is a loading, there is an unloading and then reloading. That means that I will go like that, I will come like this and then again go like this. Okay. So, again go in the sense that from this point I would go to this point. Then my sigma y is not this initial sigma y, but what has been updated. So, in other words, I have to update the yield strength of the material as well. It's a very important point that yield strength of the material is also updated. So, when I update the stress, this goes along with it. Is that clear? That is why I said sigma n. So, from here to here, the procedure is exactly the same. So, this is the reason why we say that the behavior of elastoplastic material depends upon the history of loading. What do I mean by history of loading? I have loaded here like that, unloaded, reloaded, that is the history. There is no one unique relationship between stress and strain. I can't say if this is the stress and then that is the strain, no. This can be one. I unload, reload, that can be another, and so on. So, there can be a number of situations or number of strains which would satisfy the stress. Is that clear? Okay. So, that is why I said that we will compare sigma e and see whether that is greater than sigma y. So let me say that it is yes. Yes.
So in this case, then there won't be any point below the curve which can't be accounted for, in the sense that that will always lie in one curve, like unloading.
Absolutely. So in other words, the points will always lie in a curve. This is what is called consistency condition. Okay? So it will lie only in a curve, right, in this case. In the multi-axial case, we are going to define, already you know what is yielding. So we are going to define an yield surface. And we are going to say that a point will lie either inside the yield surface or on the yield surface. A point cannot lie outside the yield surface. It has no meaning in what we call as rate independent plasticity. I am introducing a lot of terms as I explain. Note these terms. Okay, I said history dependency, in other words, the stress or the strain depend upon the history, and I now said I used a term called rate independent. In other words, the behavior that we are right now seeing and what you are looking at is a behavior where strain rates have no role to play. The strain rates have no role to play. It is only the plastic strains which have a role to play. Where are the situations when strain rates have an effect? Yes? Yeah, that correct, but in solids, you answer that fluids have an effect. Viscoplasticity. Okay, so whenever we have a situation where the temperatures are high, then we go over to a constitutive equation or relationship which is rate dependent. We call this rate independent, we call that as rate dependent or viscoplasticity, where strain rates have an effect on the yield strength of the material and further behavior after the initial yield. Right. In viscoplastic materials, the situation is slightly different. Let's not worry about it right now, but for the case we are considering, okay, for rate independent case, the material point or the stress, state of stress at a point should lie on the yield surface. We'll come back to this. We'll maybe after a couple of classes, maybe next class or after that, we'll come back to this. And let's see what we have to do in this case. Let's come back to this figure. Okay. What do we do with this? Can you have any clue? That is, I'm going from here to here. Yes, the first point is that I have to change a function at a point which lies between the two. So in other words, my calculations are okay till this point, but after that my calculations are not going to be correct. So I have a region, okay. So that's anyway, that is epsilon, delta epsilon, okay, at a particular iteration. Note that carefully. We are in one iteration, okay, one iteration. We have departed from that one place. So if this is delta epsilon, then, and this is delta sigma E, a part of it has to be corrected and another part need not be corrected. Okay. So let us say that this part, okay, this part here which has to be corrected is called R into delta sigma E. Oh, sorry, that is this part. That's the whole race here. Let me redraw it so that remove all these frills and redraw it. That is the total delta sigma, and that is the extra delta sigma that is there, and that is what I have to correct it. Is that clear? No? Okay, now 1 minute, let me draw a bit. That's the total, right? What is this? This is delta sigma E, right? And that is the part which I have to correct. I have to correct. Let me call this as R into delta sigma E. Okay? So 1 minus R, which is this part, delta sigma E, I need not correct. I can leave it as it is. Is that clear? So my first job is to calculate R. In this case, R is less than 1. So that sum of this and this will give me delta sigma E. Now this is my sigma E, that is the total elastic prediction, right? And that is my sigma N, and that is my sigma Y. Those are the things I know. Okay? Right. How do I now calculate R?
The ratio of sigma E minus sigma Y.
Very good. R is equal to sigma E minus sigma Y. Sigma E minus sigma Y divided by, yes, sigma E minus sigma N. So that I can calculate. So sigma E minus sigma Y will get, I'll get it.
How can I calculate sigma Y?
Sigma Y is already known. It is the yield strength of the material, which is the previous step, right? So this is already known. This, from this only I am going ahead. So this is known to me, and this is what I calculated. So all these things here are known to me. Okay? So I have to now bring this point down. I don't know this point, right? So this is what I have to correct. Now how do I correct that?
Sigma E minus R into
The first step is I have to calculate delta epsilon, okay, or split this delta epsilon as well. Right, that's the first step. So in order to do that, let me put some positions here. Say, let me call this A, B, C, D, E. Okay. Now that is, this total is my delta epsilon, and this is my delta epsilon, say EP, elastoplastic, and this is my delta epsilon E. Yeah, this is straight line. ABD is in a straight line. Now my whole idea is that if I calculate delta epsilon EP, then I can calculate this point very easily by calculating ET at this point, okay, in which case, this case it is only one value, and multiplying by delta epsilon EP. Is this clear? Okay. Now how do I do that? How do I calculate delta epsilon EP? What is that I know? I know R, I know this. I know this height, I know this height. That's the clue. I know this height, AC, I know AE. So how do you calculate? Yes, what is the principle? That means that ABC and ADE are similar triangles. Okay, so from this I can calculate delta epsilon EP, right? So BC by AC is equal to DE by AE, right? So in other words, AC by BC is equal to AE by DE. Is that clear? Right? So I can now calculate delta epsilon EP. So what is this AE by, sorry, AC by AE? You can bring the other side. AC by AE, that is R, or by 1 minus R, or you can write that down. Okay, or you can, sorry, yeah, AC by, no, AE is delta sigma E, and AC is equal to R into delta sigma E. So AC by AE is equal to R. Okay, you can calculate that. Now with that you can calculate delta epsilon EP, now which happens to be now equal to what? R into delta epsilon. Okay. Now once I calculate delta epsilon EP, my job is very simple. I'll just remove it here and write that down. I multiply this delta epsilon EP by ET and write delta sigma EP is equal to ET into delta epsilon EP. So that sigma at n plus 1, okay, for this iteration is equal to sigma at n plus delta sigma into 1 minus delta sigma E into 1 minus R plus delta sigma EP. Now let's recapitulate. There are a lot of things we did. Let's recapitulate what all the things we did. Okay, first we are looking at one case, elastic to elastoplastic. That's the most complicated case. Now what we said was that because of my elastic predictor, I went from D to A, which is not the correct position. I have to now correct my A. Okay, I realize that I've crossed the yield point. But I need not correct the whole of this jump, the whole of delta sigma E I need not correct. I need to correct only a part of it. Okay, let me say that this part, what I have to correct is say R, right? So R, so that this to be corrected part AC is equal to R delta sigma E, and the part which I need not correct, which is CE, is 1 minus R into delta sigma E, right? So I see that my calculation of R is very straightforward, and that is equal to AE or AC by AE. I know AC because I know this, I know sigma y, and I also know AE because that is nothing but sigma E minus sigma n, right? So I calculate R. So once I calculate R, I know this, no problem, okay? But I have to do some correction here. How do I do that correction? I find out of the total delta epsilon, which I have completely invested in the elastic case, what is the part which actually is the elastic case, and what is the part which is the elastoplastic case? The procedure is very straightforward when you look at the geometry of this figure, and you see that by similar triangles, what I have to do is to multiply this R and delta epsilon to get delta epsilon EP. So once I get delta epsilon EP, I then multiply by Et to get delta sigma EP. So once I get delta sigma EP, then I can calculate sigma, okay, that is this plus this plus this, right. Note that this, that is sigma n plus this height, which is 1 minus r into delta sigma E plus, so let me call this position as say F CF. That CF is what I will get by Et, which is the slope of the curve, into delta epsilon EP, which is this. So this multiply the slope of this curve, which is that is this curve, will give me that position. Right. Now this is actually very easy to understand after I explain it, but has a lot of problems. What if it is not bilinear, where the slope of the curve changes in the elastoplastic region, slope of the curve changes? Okay, then how do I calculate it? I have to rely on my calculation, okay, an explicit calculation. In other words, I have to rely on an explicit calculation, which means that I have to look at the slope at P and so on. So in other words, this comes into under the category of what is called as an explicit technique. Though I am not very happy right now because of the issues I have raised, nevertheless, for many problems this seems to work. And when does it work? Especially when the load steps and hence the corresponding delta epsilons are not very large. Okay, this technique seems to be okay. We have to make some adjustments, we will see that what adjustments we have to make, but many times when we are looking at problems where the time steps are small, this explicit time integration schemes, or sorry, explicit stress integration schemes are perfectly all right. Now what kind of trouble can this give? It's very simple to understand what kind of trouble it gives, and it's very easy to understand it, especially when I have a 1D curve. Now look at this curve. This is no more bilinear curve. It's no more a bilinear curve. Now I take a slope at this point. Okay, let us say that, let me draw it more flatly so that the differences are clear. So just an exaggerated case, let me take like this. Okay, now it's not very easy to find out the slope there, so let me still find out the slope at this point. Okay, now let us say I am moving from this point, okay, and I have elastically predicted and I have gone to this point. Okay, so when I correct it, where will I correct?
The line which is sloped.
Yes, line which I have drawn, this point. I will only correct to that point. So let me zoom that out. So I have two curves, that curve and that curve, and I will now, instead of falling back to this point, I will fall at that point. Okay, that means my consistency condition will not be satisfied. Right? Now what's happening here? Why is this happening? These are issues which we'll focus in the next class. Yes. Because we can't, can we solve directly for and get this point? Yes, then the equations become implicit. We will explain that in the next class, and other issues which are involved with it we will see in the next class. Yes, exactly. So ET is changing. See, the whole idea here is first to explain to you a method, then look at all the issues that come with the method. Okay? So we'll stop here and we'll continue next class.